This is the screencast for section 5.4, example 4. We're going to use double angle identities to solve algebraically some trig equations. Now the difference between proofs and solving is a proof, the left side will always equal the right side. So when you graph them, they have the exact same graph. When you solve, the sine of 2x and cosine of x, for example, in example 4 here, are only equal for a certain value or a few certain values of x. So their graphs look totally different but will intersect. So we can't prove that the sine of 2x will always equal the cosine of x. We are going to solve for the values where they are equal. In terms of Algebra 1 and Algebra 2, anytime you solve an equation, you set it equal to 0. So, maybe not anytime, but a lot of times. And that's going to work out here. So I'm going to subtract cosine of x from both sides. So I have sine of 2x minus cosine of x equals 0. Now, of course, the directions gave us a clue. Use double angle identity. But I see a sine of 2x here, so I am going to convert that to its equivalent expression to sine of x cosine of x minus cosine of x equals 0. Now I can factor out from both terms before and after the subtraction sign a cosine of x. Now, because my expression on the left side of the equal sign is completely factored, I can use the zero factor property. The cosine of x has to equal 0, or 2 times the sine of x minus 1 has to equal 0. Well, if the cosine of x has to equal 0, and I'm only looking for angles between 0 and 2 pi, we've done this in section 5.1. We're going to solve for the angles whose cosine is 0. So x has to be pi over 2. That's a pi. Or 3 pi over 2. Now here I would add 1 to both sides, divide by 2, and find out where the sine of x equals positive 1/2. Well, there are two values where sine of x is positive 1/2 between 0 and 2 pi, one rotation on the unit circle. That's pi over 6 and 5 pi over 6 in quadrants 1 and 2. So usually your book will write these in increasing order. So going around the unit circle, the first angle I would hit is pi over 6, then pi over 2, then 5 pi over 6, then 3 pi over 2. So those are my possible x, those are my x values where the sine of 2x does equal the cosine of x in increasing order. The now try problem example, or sample 23, exercise 23. The cosine of 2x plus cosine of x equals 0. This one's already solved for 0. Nice. Now I'm going to pick an expression for the cosine of 2x that would help me out in this situation. Now the cosine of 2x can be expressed in 3 ways. So I have to pick one that's going to help me, not make things more complicated. So I'm going to pick the 2 cosine squared of x minus 1. Now I can factor out, no, I cannot. I'm going to rearrange this because I see 2 cosine squared of x plus cosine of x minus 1, 3 terms in this problem. Well, I'm going to use my u substitution again. I'm going to make cosine of x u so that I can write this in a way that's easy for me to understand and factor. So now if I use the quadratic formula, u equals the opposite of b plus or minus the square root of b squared, no, b squared, minus 4ac all over 2a. I'm not going to sing the song, don't ask. So u equals negative 1 plus or minus the square root of 9, actually, over 2. So that's going to be negative 1 plus 3 over 2, or negative 1 minus 3 over 2. So that's going to be 1/2, or negative 1. Well, u is cosine of x. So cosine of x equals 1/2, or cosine of x equals negative 1. The x values where cosine is 1/2, those are pi over 3 and 5 pi over 3. Again, one rotation, we're looking at one rotation of the unit circle between 0 and 2 pi, so cosine is positive in quadrants 1 and 4. And then the x values where cosine is going to be -1, that's only 1, that's just pi. So now, in increasing order, the x values that make the cosine of 2x plus the cosine of x equal to 0 are pi over 3, pi, and 5 pi over 3, in increasing order as I rotate around the unit circle.